तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class we were exposed to the frequency limitation of amplifiers. Let us consider this example now, which illustrates how the so called gain characteristics of the amplifier gets limited. Determine V0 over Vs, V0 over Vs, that is the amplifier gain for the amplifier shown, wherein apart from the usual input impedance, source impedance, output impedance and the load impedance, we have the effect of stray capacitors, one at the output 10 picofarad, one at the input 50 picofarad. The input capacitor total together comes out to be 50, let us say, and the output capacitor comes out to be 10 picofarads. This is the typical order of the amplifier capacitors. Now, under this circumstance, I would like to know V0 over Vs. Now, you can write down the different loop equations etc. and solve it, but I would like to solve this by just observation. In all these cases, I have told you that the amplifier gain comes out as K0, which is independent of frequency, divided by 1 plus S tau I, 1 plus S tau naught. This is the input time constant, tau I is the input time constant, K naught is the DC gain. We have discussed independent of frequency, right? DC gain, and tau I is the input time constant, and tau naught is nothing but the output time constant. So, for any amplifier this can be written this way. If there are two time constants, if there are three time constants, let us say you have one amplifier cascaded to another amplifier, then there will be an input time constant, an intermediate time constant and an output time constant. If you have instead of 2 stages 3 stages, then correspondingly there will be 4 time constants. Okay. If there is a single stage, okay, there will be 2 time constants at least. Two stages, 3 time constant, okay, input, intermediate, output. 3 stages, 4 time constant. N stages, at least n plus 1, okay, time constants will be there. So this is something that you can, okay, remember that depending upon the number of stages we can say what is the order of the system. This is called first stage. If it has 2 time constants, it is called a second order system. second order. This is a third order. This is a fourth order. Amplifier system. The order of the system is dependent upon the number of time constants. Okay? The first stage is already a second order system. There is nothing like first order at all in this case. Second stage corresponds to third order minimum. Third stage corresponds to fourth order system. So, the order depends upon the number of poles. These are called poles of the system. These are called the poles. There are no zeros here. Okay. These concepts you have learnt in your control engineering. These are called poles of the system. The poles are located at omega equal to, or actually S equal to minus 1 over tau I S12, okay, and 1 over tau naught. Equate this to 0, you will get the pole. S is equal to minus 1 over tau I is one pole and minus 1 over tau naught is the other pole. The poles of this system always will lie on the negative real axis. Okay? Poles of these such systems will always lie on the negative real axis. This corresponds to negative real axis. Okay? So, of the S domain. S domain has real part and imaginary part. In that, it will lie on the negative real axis. So, this is a two pole system or a second order system. Okay? There are two time constants connected with this system, and we have obtained the Bode's plot in the last class. We have seen that the Bode's plot for the magnitude of V naught over Vs versus omega will look like these are asymptotic. K naught, it is independent of frequency at low frequencies. At frequencies much lower than 1 over tau I and 1 over tau naught, the constant equal to K naught, and then it will decrease at, we have discussed this, 20 decibels per decade. 20 decibels per decade, and then the next time constant will bring about 40 decibels per decade attenuation. All these things we have understood. Okay. So, assuming that this is the dominant time constant and this is less dominant, okay. So, we can say that, for example, if tau I is much greater than tau naught, then this corresponds to omega equal to 1 over tau I, and this corresponds to omega equal to 1 over tau. These are called corner frequencies. In the last class we have understood, these are called corner frequencies. This fall off is at 20 decibels per decade, this is at 40 decibels per decade, or 6 decibels per octave, 12 decibels per octave. Okay. So, this is what we have seen. We have understood how, therefore, the frequency response characteristic of any amplifier will change. Now, let us take this for the example that is chosen, how much it is going to be. What is K naught? How do you evaluate K naught? Now, I would not like to write down any equation. Look at this circuit. K naught, you forget about the existence of the capacitor, right. it is frequency. So, Vi is going to be half of Vs, because you have 10k here, 10k here. Vi is going to be half of Vs. Again, that half of Vs is going to be multiplied by 100. So, 50 times Vs appears here. That 50 times Vs again is going to be halved, because you have 20k, 20k. So, you have 25 times Vs. So, k naught is 25. Again, let us go through this. Vs is going to be halved and appears here as Vs by 2. So, Vi is equal to Vs by 2. So, Vi equal to Vs by 2 for the example. So, 100 times Vi becomes 50 Vs. This 50 Vs is again divided equally between 20k, 20k, appears as 25 Vs. So, k naught is equal to 25. So, just by observation we are now able to write down the value of k naught for this example. Next, what is tau I? I have told you tau I is equal to Ci, this capacitor, okay, into effective resistance across it, which is 10k, you short this, and 10k, which is 10k parallel 10k is 5k. So, you have Ci into 5k, which is 50 picofarads into 5k. Which is nothing but 250 into 10 to power minus 9, or 250 nanoseconds. That is the time constant of the input. So, tau I is known. Tau naught similarly is nothing but C naught, which in this case is 10 picofarads, and again short the sources. So, 20k parallel 20k is the effective resistance across the capacitance, which is 10k. 20k parallel 20k is 10k. So, which is 10 picofarads once again this is equal to 100 nanoseconds. So, we have solved the problem. So, I can write down the transfer function V naught over Vs as 25 divided by 1 plus S into 250 nanoseconds 1 plus S into 100 nanoseconds. So, that is the answer. Now, I would like to expand here. Suppose we plot the Bode's plot, then this corresponds to gain of 25 remaining constant. Okay. If you convert it into decibels, it will be 20 log to the base 10 of 25. Okay. That is the decibels, 20 log to the base 10 of 20. Whatever it is, that is the gain, constant gain at low frequencies, and then at one corner frequency corresponds to 1 over 250 into 10 to power minus 9, or omega 1, we will call it omega I, corresponds to, this is omega I, this is omega naught. So, 1 over 250 nanoseconds, or this is equal to omega I equals, therefore, 1000 divided by 250, that is 4 into 10 to power 6 radians per second, or 4 mega radians per second. 1000 divided by 250 is 4 into 10 to power 6 radians per second, that is omega I. Similarly, omega naught is going to be 1 over 100 nanoseconds, or 10 into 10 to power 6 radians per second. So, we have got the corner frequencies also for this so called Bode's plot, and this is the complete frequency response of the circuit. 4 is comparable to 10. So, suppose I ask you to determine the upper cutoff frequency of this. Upper cutoff frequency or upper 3 dB frequency is going to be defined, I told you clearly, if this corner frequency is far away from this, then this itself is the upper cutoff frequency, because this does not influence this. But now in this case 4 and 10 are pretty close to one another. So, upper cutoff frequency actually is going to be less than 4 mega radians per second, because at this particular point, apart from the influence of this also is going to influence in reducing the gain. So, you have to evaluate the upper cutoff frequency for this. How do you evaluate this? This is very simple. Upper cutoff frequency, we have also said, is nothing but 3 dB point, upper 3 dB point, where the gain falls to 1 over root 2 times the maximum, the low frequency gain. So, if the gain of this is 25 by this, then when the gain falls to 25 by root 2, that is the frequency correspond to upper cutoff frequency, right. So, we will see that if omega I and omega naught are comparable, then 25 by 1 plus, let us say, j omega s, right, j omega by omega I, 1 plus j omega by omega naught is the actual gain. The magnitude of this is going to be 25 by 1 plus omega by omega I squared under the root, again under the root 1 plus omega by omega naught squared. So, when this becomes equal to 25 by root 2, that frequency corresponds to upper cutoff frequency. So, 25 gets cancelled. That means, when this whole factor becomes equal to root 2, so we can square this. So, 2 becomes equal to 1 plus omega by omega I whole square into 1 plus omega by omega whole square. So, this is going to be a quadratic equation, which if you solve will give you the upper cutoff frequency. So, I would like you to work this out, solve this quadratic equation. This is a quadratic equation in omega by omega naught, omega squared, right. You get omega to the power 4 and omega squared. You can solve for omega squared and get the upper cutoff frequency here. So, please, as a homework problem, complete this. That is not part of the example problem. Obtain the upper cutoff frequency for the example. Obtain the upper cutoff frequency for the amplifier. So, So, you will notice that the upper cutoff frequency is going to be less than the lowest of the corner frequencies. So, let us consider the example 6. An amplifier has V naught over Vs given as 100 by 1 plus S by pi into 10,000. That whole thing multiplied by 1 plus S by pi into 10 to power 6. So, this is the characteristics of the amplifier. You are asked to find out its bandwidth. Now, I have told you earlier that upper cut off frequency is the same as upper 3 dB frequency, also same as half power point, upper half power point, also known as upper half power point, upper TDP frequency, upper cutoff frequency, all are one and the same. Now, in a situation where this particular frequency is dominant compared to this is its influence is far away. This is the first frequency which comes into picture. So, this dominates the attenuation characteristic of the amplifier, and this becomes of no significance. Therefore, even though this is a second order system, this can be equated for practical purposes within the range of interest. It is only 100 divided by 1 plus S by pi into 10 to power 4. So, this is how we can approximate. This is 10 to power 4, this is 10 to power 6, there is a 100 magnitude difference. Okay. So, we can ignore the effect of this within the useful range of the amplifier. So, even though this is a second order system, in effect we can, as an amplifier, we can consider it, approximate it as a first order. That means, when the next corner frequency is an order of magnitude different, that is 10 times higher, then you can approximate the system as one order less, first order. So, please remember that. So, if the frequencies, corner frequencies are far apart from one another such that they are 10 times, okay, then it can be considered that the other one, far away one, can be ignored within the band. So, 100 divided by this, and then the bandwidth becomes because S is equal to j omega is substitute, and this whole quantity should become equal to 1. That means that is the bandwidth. So, bandwidth becomes equal to this itself. So, if you want to convert this into frequency, radians per second to hertz, then you have to divide it by, so in terms of hertz, so this is going to be pi into 10 to power 4 divided by 2 pi, or this is equal to, okay, pi gets cancelled, 5 into 10 to power 3, or answer is bandwidth is equal to 5 kilohertz. So, bandwidth, this is an important parameter associated with an amplifier, okay, is essentially the first corner frequency if other corner frequencies are far away from the first corner frequency. Otherwise, as will be given out in your example, okay, problem corresponding to example 5, okay, it will be dependent upon the other corner frequency as well. In normal cases, the first corner frequency is the dominant time constant, which is going to therefore fix up the bandwidth primarily this way. So, 5 kilohertz in this case is the bandwidth of the amplifier. That means the useful range wherein the signal is not going to be much getting affected due to frequency, that range corresponds to 5 kilohertz. So, this is an important parameter associated with amplifiers. What does it mean? At 5 kilohertz already attenuation is going to be by 3 dB. At 5 kilohertz, if you see, this becomes j, 1 plus j. So, attenuation becomes 3 decibels. It goes to 1 over root 2, half power. So, beyond that, okay, it is of no interest to us. So, that means all frequencies beyond this will be subjected to more attenuation, okay, and therefore will get distorted. This is called frequency distortion. What is it? That means for frequencies much less than 5 kilohertz for the example, okay, all frequency components in the example, okay, the amplification factor is equal to 500 in this case, remains constant 100, whereas frequencies around 5 kilohertz and much beyond 5 kilohertz, it is going to be different for different frequencies. So, the input signal, if it is comprising of many frequencies with certain amplitudes, the same amplitude ratio is not going to be maintained at the output. That is what is called distortion. Let us say we have say 100 hertz signal and 100 kilohertz signal at the input. 100 hertz signal is definitely going to be amplified by 100, but 100 kilohertz signal is going to be attenuated and its amplification factor is going to be much less. So, the ratio of the amplitudes of 100 hertz and 100 kilohertz will not be maintained at the output, which means what is going to be available at the input will be distorted at the output. The shape is going to change. Not only that, this is amplitude distortion. Okay. Further, these different frequency components will be subjected to phase shift also. As I told you, at 5 kilohertz, the phase shift suffered is going to be 45 degrees. 1 plus j corresponds to 45 degrees. Already there is a phase shift of 45 degrees. So, different frequency components will be suffering different phase shifts. Okay. So, this phase shift will cause the signal to be distorted. Okay. So, both amplitude distortion, okay, and phase distortion will occur because of the frequency dependence of gain. So, it is necessary that we must make sure that when we amplify signals, in this particular case, for this example, the signal frequency component should not be beyond 5 kilohertz. Its useful range is only about 5 kilohertz. Okay. So, otherwise if you have signals to be amplified which contain frequency components which are higher than this, we should have an upper cutoff frequency or bandwidth of the amplifier which is much beyond whatever signal maximum frequency signal has. Okay. For example, video amplifier, if it is that we are designing, then the frequency components in the signal will be up to about megahertz. That means upper cutoff frequency of that amplifier should be corresponding to tens of megahertz, so that no distortion occurs in the signal. If it is an audio amplifier, maybe the signal frequency components of interest will be only about 20 kilohertz, the best audio amplifier, let us say, and therefore the upper cutoff frequency need to be only about 20 kilohertz. So, this is the essence of frequency distortion. Because of frequency dependence of amplifier gain, we have distortion if we use amplifier for amplifying signals beyond its capability. Okay. So, we should always restrict amplifiers use within its bandwidth. Now, this frequency distortion will be causing amplitude distortion. What is amplitude distortion? Different frequency components will be subjected to different attenuations. Okay. That is why amplitude distortion is caused. Then there is phase distortion. What is phase distortion? Different frequency components will be subjected to different phase shifts. Okay. That is going to cause phase distortion. So, both these cause frequency distortion. Okay. Apart from this, we have now some other aspect that we have to touch upon as far as amplifier performance is concerned. This is different from what we have been discussing so far. What is this? Consider an amplifier. Amplifier is a block. Okay. So, output is going to be related to input. Let us consider V naught. A voltage amplifier will consider. It could be current amplifier, I could as well consider I naught, okay, or anything. It is a function of, okay, input voltage, let us say. I am considering, let us say, voltage amplifier. Strictly speaking, in general, any device will give me an output which is a function of Vi, not just necessarily proportional to Vi. So, if it is a general function of Vi, then that function can be split up as something, let us call it as a voltage which is going to be called offset. Okay. This is independent of the input voltage. This is a voltage which is independent of Vi. That voltage is called, as you already say, it is called offset voltage. In an ideal amplifier, we do not want to have this kind of offset voltage, right. In an actual amplifier, this might also be called quiescent voltage. You have to get rid of it by decoupling it by means of a capacitor. So, this offset voltage is either called quiescent point voltage or offset voltage, depending upon your design of amplifier. This is independent of Vi. Then something that is going to be K naught into Vi. This is what we have been calling as voltage gain. This K naught is the factor that we have been calling as voltage gain. Linear dependence upon Vi. Then something that is going to be K1 times Vi square, then K2 times Vi cube, so on. These terms are called non-linearities. These are the non-linearities, right. It is supposed to be only dependent upon Vi, but the block that we have got, the active device we have got, okay, is something that simply gives you a function of Vi. So, in general, any amplifier that is designed by anybody will only give you output voltage or output current as a function of input voltage or input current. Okay. That can only have an offset, okay, voltage which is independent of Vi, then something that is linearly dependent upon Vi, that we call as voltage gain, plus terms which are non-linear terms, it will be Vi squared, Vi cubed, Vi. Now, in a good amplifier, what should happen? The offset should be as small as possible, it should go towards 0, and then K1 should be 0, K1, K2, etc. All these things should be going towards 0, and K0 should be as constant as possible, as stable as possible. So, K0 is something that should be as stable as possible. Offset should go towards 0, K1 should go towards 0, K2 should go towards 0, all the nonlinearities should go towards 0. So, amplifier nonlinearities cause again distortion. This has nothing to do with frequency. This has only to do with amplitude of the input signal. Okay. So, this distortion, this depends upon where exactly we are operating the amplifier, so called amplifier. We can therefore select the operating point of the amplifier, we will select the operating point of the amplifier in such a manner that the offset is 0, K1, K2, Kn are as small as possible, or we will select the device for designing the amplifier in such a manner that this is valid. That means, after selecting the device, then we will select the operating point for the device. That means, biasing of the amplifier is done in order to make the device work in a region where the linearity is dominant, K0 is dominant. Okay. This should be maximized, okay. K0 should be maximized, and K1, K2 and Kn should be minimized. This is the, it indicates this should be minimized, they should be maximized. So, we will bias the active device, or we will select the operating point of the device, or we will design the circuit, okay, the complex circuit containing large number of devices, active devices, in such a manner that this whole thing is true. So, design of an amplifier involves, okay, selection of the operating point and the bias in such a way as to make the nonlinearities the minimum, linearity the maximum, okay, and offset voltage the minimum. If you have the nonlinearities coming into picture, that will cause distortion. So, if Vi is a sinusoid, for example, Vi squared will become sin squared. So, it will have harmonic components. At the input there was no harmonic, it is now generating a harmonic, okay, at the output. Vi cubed will generate a third harmonic, Vi to the power 4 will generate the fourth harmonic, like that. So, that means all these nonlinearities will create unwanted components at the output. So, that causes distortion. If it is a sine wave at the input, output will no longer be a sine wave, it will have all the harmonic components also present. That is what is going to be causing distortion. So, this part of the design is going to take up lot of time for us. After identifying the device, how to bias the device, okay, how to arrange these different circuits in such a manner as to make the offset 0 and make the nonlinearity minimum and maximize the linearity. That will be the purpose of most of the design lectures of the future, right. So, this is the case for an amplifier with input port and output port. Okay. The input port may be the two terminals, okay, of a differential stage. That means, you can also call the input port of the amplifier, instead of always referring the voltage with respect to this, you can call this as E1 and this as E2, and E2 minus E1 as being equal to Vi. Okay. So, that means now it becomes a differential input operation. That means, voltage reference can be taken with any point, arbitrary point, and these two voltages can be taken as absolute values from that arbitrary point. Earlier we had taken the voltage reference as from here, okay, Vi, and for this from here. Okay. So, if you take these voltage references as from an arbitrary point, then this becomes a differential input. Okay. Similarly, if you take this from an arbitrary point, the same arbitrary point, this will become differential output. So, this becomes a differential input, differential output amplifier. If the voltage reference, this is only a concept, okay, is shifted somewhere else. So, in a 2-port amplifier, this thing you can treat it as differential input and differential output amplifier. Okay. So, what all we have said is valid, whether it is differential input and differential output amplifier or just one port, okay, with this as common terminal. That means, actually this becomes 4 terminal, okay, becomes 3 terminal now, because we are connecting these two together and using this as a reference. So, this becomes a 3 terminal amplifier. If this is not there, then it is a 4 terminal and 2 port amplifier. Right. So, these discussions that we have had is going to be perfectly general, right, and it is valid for 3 terminal as well as 4 terminal amplifiers. Okay. These are only conceptual references. Now, if you take arbitrary reference here, this will become differential input and differential output amplifier. So, E1, E2, let us say E3, E4. So, E3 minus E4 is what we have been calling as V0. So, finally, I would like to indicate that the amplifier works with power delivered from a separate source, which is always called the DC power source. Right. So, for biasing we require a DC supply. So, this DC supply delivers the power required for biasing the amplifier. So, this DC supply, let us say, is plus Vs and minus Vs, then it is called dual supply. Why do you go for dual supply, plus Vs and minus Vs? Suppose this signal could be positive or negative, Vi could be positive or negative. Then in order to obtain this, okay, we have to have both plus and minus supplies. The operating point should be such that output should be 0 when the input is 0. So, which means necessarily, in order that the offset of this is 0, we must operate the output at a voltage which is equal to 0. With plus Vs and minus Vs, the quiescent operating point for this should be 0. So, that is what requires a dual supply. We can have single supply, then it will be Vs and ground 0 or minus Vs and 0. Then obviously, the operating point in order to have maximum range for the output signal can be minimum equal to 0, maximum equal to Vs. Here also output signal could be maximum equal to plus Vs, minimum equal to minus Vs. This is what is called the range for the output signal. Beyond this point, the output is said to go to saturation. This is another limitation. So, apart from these limitations, we also have what is called saturation. Let me again explain this in terms of figures. This is V naught, this is Vi. This is the output input characteristic of this amplifier, let us say. It should be, ideally speaking, linear. This is linearity, okay. V naught and Vi should be linearly related, that is V naught is equal to K naught times Vi, this is the line passing through the origin. If it does not pass through the origin, it will be this, or it could be the other one. So, if it does not pass through the origin, this voltage is called the offset voltage, this or this. When Vi is equal to 0, there is an output voltage, this is called the quiescent point. So, if it does not pass through the origin, then we are said to have an offset voltage. Now, that is clear what is offset voltage. There could be non-linearity, that means it is not going on being linear, it is going to a non-linear region, right. The delta Vi by delta V naught by delta Vi, the slope here is the same as the slope here, is the same as the slope here, but here the slope is less. So, this is called the non-linearity. This is the linearity. This is the offset. Then ultimately it will go to what is called saturation. Let us say this is the maximum voltage your output of the amplifier can give, this is the minimum voltage the output of the amplifier. This is called saturation. Beyond this, output is not going to change, beyond that output is not going to change further. Even if the input is changed any by amount, output remains constant, output is limited. So, output gets limited. So, if power supplies are used for biasing, normally these are the limits, plus Vs and minus Vs. It is made symmetric so that the quiescent point could be 0. So, we have learnt a lot about distortion. That means, distortion occurs because of Vi increasing, and then the further increase in the output voltage is not the same as the earlier increase for the same amount of Vi change. So, that is called non-linearity. Then there is a region beyond which further increase in Vi does not cause any change in V naught, that is called saturation, right. That can occur both on the higher side as well as the lower side. So, saturation non-linearity, the non-linearity because of the device, this nonlinearity. These are this kind of nonlinearities. In fact, if the nonlinearity that I have put down here, it is symmetric here, that simply means that K1 is 0. You can test it out. K1 is 0, K2 is present. This is going to have this kind of nonlinearity, which is symmetric both for positive going and negative going signal, okay, has K1, okay, K3 etc. going to 0, but K2, K4 etc. existing, right. So, this is one type of nonlinearity. So, that depending upon the device that you select, the nonlinearities will change. So, in the next class we will learn more about these aspects, distortion, what does distortion cause, okay, how distortion can be measured, okay, quantitatively etc. This distortion that we have talked about for the second time is different from the frequency distortion, okay, which comes about because of frequency dependence of the gain.